Thank you, Ila, and thank you for everyone for organizing this wonderful event. So, like Ila said, my name is Chen Amiraz. I'm from the Department of Computer Science, and my research focuses on statistical machine learning. And today we're going to learn how 1,000 little failures can turn into success. I know this title may send you in some different directions, but it will all become clear shortly, so bear with me. An abundance of data is being processed at this very moment by distributed learning algorithms. One example, which many of you may have used on your way here, are routing applications like Waze, where each user sees its own local view of the traffic and then sends it to the application servers, which aggregate it and give back an optimal route for each user. A completely different example, which we touched upon in Eden Ifrach's talk this morning, is an example involving medical data, where a researcher contacts many institutions like hospitals or HMOs in order to see their electronic medical records, and they send it back to the researcher so she can learn from them. While these examples are completely different, they can both be modeled in the same way, by a network of many, many machines that all communicate with a fusion center or a cloud. Each of these machines sees a different sample, and the goal of the fusion center is to jointly learn from these samples. So what are the challenges in distributed learning? So in both of these examples, you can see that that one problem can be communication constraints. So if the volume of data being sent is very large, like, for example, in the Waze example, you can think that it might take a really long time for you to find what turn you need to take next. Or in the medical data example, you can think that patient files are huge and have tons of information about each patient, and you can multiply it by millions and millions of patients. This can be very expensive in terms of communication. And another challenge, which is exemplified in the medical data example, is privacy. We don't want to send the data itself. We want to somehow learn without sending the data or the samples themselves. So my PhD focuses on distributed learning algorithms, which provably overcome these challenges. And what we'll see today is an example of that, of a recently published paper of ours, where the algorithm solves a distributed learning problem, and it is both communication efficient and private. So now let's do a short experiment. This room will simulate a distributed system, and the question is, what do you see in this image? So this is what we call a noisy image. It has a lot of different pixel values are noisy. And to make it easier, I'll even give you 3 options. It's either a squirrel, an elephant, or a koala. So who thinks it's a squirrel? Okay, some of you. Very few. Who thinks it's B, an elephant? Okay, about 10%. Who thinks it's C, a koala? Okay, very nice. So you're all very good as denoisers, just so you know. I asked this in a different conference, and the answers were a bit different. So if I gave you a different sample of the same noisy image, would this help you? So here, the instantiation of the noise is different. The underlying image is the same. So what some of you might say, as usual with noise, let's take both these images and average them together. Maybe we'll be able to see something a bit more. So this is like averaging information from 2 machines that have different noisy samples. And we can do this to 4 machines, or 16 machines, or even 100 machines. And at some point, you will understand that it is indeed C, a koala. So due to noise, it was hard for us to recover individually what is going on inside this image. If I didn't give you 3 options, I'm sure it would be much harder if I gave you like 100 options. But if we communicate, we have a better chance. So let's look at our challenges again. So here we got different noise realizations. So we got different noisy images, and we'd like the Fusion Center to identify what's in the image, but specifically we're talking about statistics, so we want to recover the image itself. So if we send the images to be averaged in the Fusion Center, this would take a lot of communication. So it's the sample length, which in our case is the number of pixels in the image, times the number of machines, which can be really huge. And also in terms of privacy, we're sending the samples themselves, so this is clearly not private. So one solution, which we study, is using voting schemes. So we're sending a short representation of what's going on in the image, which is the votes, which on one hand allows us to save communication. So in our talk, we will see it will even be shorter than the sample length, so even shorter than sending one such image. And also in terms of privacy, since you only send votes, you don't give a lot about what's going on in the image. So why can we save communication? So there's this notion called sparsity, which means that you can represent a signal with very few non-zero values. So in the koala case, if you do this representation, you get this image. If you zoom in, you will see there are very small areas that are white. And what's going on here is that the black areas are areas where the values are very close to zero, and the white areas are where the values are large. So essentially, this is how compression algorithms like JPEG work. So what you see up there is the original picture of the dog, and what you see down there is only using 1% of the values in the image. So everything that's close to zero, you think it's actually zero, and only 1% is being saved, and you can still understand pretty well that it is indeed a dog. So another way to represent this, instead of the picture we had before, is to think that we have some unknown sparse vector. So what this means is that all of the white locations are zero, or indices are zero, and there are only k non-zero indices indicated here in green. And this is what we want. This is what we'd like to recover. And basically, the idea is that we can save communication using sparsity. So what happens when there's noise? In this case, the noisy image can be represented by a sample, which is this unknown sparse vector plus noise. And like we said, we want to recover these. And the noise is Gaussian, which means it has this bell-shaped form. But due to noise, a single machine cannot detect the non-zeros on its own, because you see there are values everywhere because of the noise. So to recap what we want to do, as input, we get different samples, which are the noisy koala images, and we want to output the koala. But we use this representation, so basically we have these noisy samples, and we want to find the k non-zero indices. And like we said, our goal is to have small communication, smaller than the signal length, and it will be private, so it will only send votes. What our algorithm does, so each machine votes for the k indices with the highest representation values, and then the center aggregates these votes and outputs k indices with the highest number of votes. So notice a few things. First of all, this algorithm is pretty simple. I could explain it to you in less than a minute. It's also pretty simple to implement. It's private in the sense that it only sends the votes, the locations of the non-zero values, and not the values themselves. And it's fast. It's also pretty fast to compute, and also it only requires one round of communication. In terms of communication, what we proved in our paper, if you look at this graph, on the x-axis, you see the signal-to-noise ratio, which is the strength of the signal divided by the strength of the noise. So as you go along the x-axis, the signal is stronger compared to the noise. And with the y-axis, you have the number of machines. So in this red area, you would fail even with infinite communication, because there is simply too much noise to recover the signal. In this green area, even a single machine would succeed with high probability to recover the signal because the signal is very strong. And what we proved is that there is a wide area of SNR values where our algorithms succeed with high probability, and the total communication is even smaller than the sample length, even smaller than sending one of these images. So let's see a simulation result. In this simulation, we have 1,000 machines. The dimension of the signal is 5,000, and k equals 1, so we only want to recover one index. And in the simulation, the non-zero index is 400. So notice that each machine only sends one vote. What you see here is the index number and how many votes it received. So for example, index 1100 got 0 votes, and many indices got 0 votes because there are only 1,000 votes for 5,000 indices. Index 29,000 got 2900 got 1 vote. Index 2122 got 3 votes, and the special index, the non-zero index 400, got 5 votes. So on the one hand, it got 5 votes, and everyone else got at most 3 votes, so we could identify it by taking the maximum one. But on the other hand, out of 1,000 machines, only 5 machines voted for the correct index, which means that 995 machines were wrong. So 99.5% of the machines fail, but our algorithm still succeeds. In terms of communication, the naive algorithm we presented in the beginning of sending everything had 5 million values. Just sending one signal is 5,000 values, and our algorithm does it with only 1,000 votes, which is only 0.02% of the naive algorithm that we presented in the beginning. So to conclude, we showed how exploiting very small advantages enables success on extremely noisy signals. And in other words, sometimes you don't have to look for Gulliver in the land of Lilliput. It is enough to only look for the tallest Lilliputian. Thank you for your attention. This is the paper. If you'd like to read more about it, it's joint work with Robbie Krautgammer and my advisors Robbie Krautgammer and Boaz Nadler, who is sitting here today. And if you'd like to hear more about it or talk to me more, this is my email. Feel free to contact me. And thank you very much.
Thank you, Chen, for the amazing talk. Any questions? Yes.
So the question was, what happens if we don't know the number of indices? So we discussed this also in our paper. What I presented here is only one example.
I'm not sure it is related, but you succeeded to eliminate the noise by averaging, by this algorithm. Is this a possible application also in the legal world? Like that the judge from all the noise, all the different judgments that has been done in different cases can decide what is the best judgment, or the computer can do that and declare the person innocent or not? I'm asking if, because this is a lot of noise in our life, legal or when we drive.
So I agree that I think that there is room to, in the case of law, there is a lot of noise that is being impacted by personal bias of judges, and different judges give different judgments. This specific algorithm wasn't designed for that, but there's like a wide area of research that looks into things like this, also in computer science. Yeah.
So often the quality of the image correlates with the time of acquisition, and you show here that you can reconstruct high quality image out of a small amount of information that you get from each one of the low quality images. So is this a way to improve image quality, say in medical imaging?
So if you had many images, many noisy images of the same underlying signal, then yes, this is what's being used. Like a lot of denoising algorithms use different images of the same image in order to, yes. But what we showed here is in a distributed setting where they don't all sit in the same place and you can't just average them. That's like the novelty.
You showed a case for 1K, one parameter that you wanted to find. How would it scale the number of computers or of senders that you need for more?
Yeah, that's a great question. So I showed k equals 1 in the simulation, but we addressed general k in the paper. As you could expect, the larger k is, the more communication you'd need to send, and it does grow linearly in k.
Let's take the speaker again.
Thank you.